So today we are going to study about Planck's radiation law. So we know that as the temperature is increased, the lambda max moves in leftwards. So uh, here the lambda is the maximum value, and for the same voltage, the bulb starts to glow red. And if the lambda is decreased, it will become white, and all the wavelength will come under this. Means here this T3 is greater than T2 is greater than T1. So lambda is the wavelength of the corresponding maximum energy, and that is described by Wien's displacement law. Also, Wien says that lambda max into temperature, that is equal to 2898 micrometer, and Stephen says that energy is directly proportional to the temperature's fourth power. Means higher the temperature, more the energy will be. So as the energy was in lambda, we can convert it into the frequency. Also, we know that lambda is equal to c by nu. If we differentiate it, so d lambda is equal to minus c by nu square dV, and u nu d nu is the energy per unit volume in the frequency range. uh, Similarly, u lambda d lambda would be energy per unit volume in wavelength range. So we can find out u lambda d lambda or u nu, that d lambda or d mu at the end cancels out. How? So finally, we if we create a black bodies, to create a sample of black body, we just need a, a box in which there is one cavity, and when the wave inserts the cavity, it forms the stationary waves. So those stationary waves create the equilibrium temperature, and the function of those energy will be proportional to nu square, nu cube, and function is of nu by t. So the Wien's radiation observed the empirical equation, that is u nu, that is equal to a constant nu cube e raised to power minus bt by nu. So because of that, it formed the uh, the exact observed curve, but that worked only for larger frequency. It did not work for smaller frequency. So Wien radiation does not work for smaller frequency. So for to sort out that, Rayleigh Jean did some experiment, and Rayleigh Jean again created the stationary wave in the box, and uh, he created the standing wave, and in the enclosure, or each standing wave is considered as an oscillating system. So he counted the number of oscillation, and that value came out to be 8 pi nu cube by nu square by c cube in the frequency range nu to nu plus d nu. And then he founded the average energy. So he got the value e raised to power minus e raised to power minus e by kt, and he found the average of it, and its value came out to be kt. So for one oscillation it came out to be kt, for n oscillation it came out to be multiplied by the number of oscillation that we found. So 8 pi nu square by c cube into kt. So this was uh, 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 Jean's equation, Rayleigh Jean's equation, but it also created some catastrophe. What was that catastrophe? Ultraviolet catastrophe. Means for higher frequency it did not work, and the Wien's for higher for lower frequency it did not work. So ideally the curve should be like that, but in Rayleigh's case, we were getting infinite value of the energy density in di by dv, and in this side we took frequency. So ultraviolet catastrophe was found in the Rayleigh Jean equation, that was 8 pi nu square by c cube into kt. So to solve that, Planck derived the quantum mechanics, and he said that every oscillator has a fixed quanta of energy, and it can be in a multiple of n only. So n can be 0, 1, 2, 3, any value. So can be integer multiple of h nu only energy. So when he said he found out the average, he said that energy, average energy will be n of h nu into minus of n h nu. To find out the average, he just integrated, he just did summation, because integration cannot be done because energy is not distributed continuously. So from here he got the value h nu divided by h nu by kt minus 1 for one oscillation, and then he multiplied it by one quanta. So this is how the energy in the Planck's found out. Thank you guys.